So let's take a look at some real stock data so we can see how actual returns are, so we can model the actual returns. So what do I have up here? Well, let's go get some. I opened up Yahoo Finance. Let's look at Home Depot, just as an example. Okay, so here's the stock trace, just giving me the prices over the last day. But let's take a look at that. Let's look at a 5-year. All right. I want to understand then what's happening here. It looks like generally the stock is drifting up, trending up. Here I can see what it closed at, 133.89, and we can do things like look at 1 month. Now, 1 month it's a little bit up and down random. 1 day, we don't have that day because it's not opened yet. But let's say a 5-day, we're looking at a week. You don't see that general trend. If I look at a 10-year, then it does look like a general trend. All right, let's actually get the data. I'm going to go to historical prices. And let's get a year of data just to work with. I'm asking for daily. The other time steps I could use are weekly, monthly. Get prices. Opens up a chart. And what we want to deal with, and so let's take a look here. The dates are the trades happen. Notice that they always put these in a backwards order, starting from the most recent and going to the oldest. We've got what it opened at during that day, the high point it reached during that day, the price, the low point it reached, what it closed at, the volume, that's how many shares traded, and the adjusted close. We're going to end up using the adjusted close. What the adjusted close is it takes into account any dividends or stock splits. So that price has been scaled that way. So let's download the spreadsheet so we can start to do some things with it. Here's all that data. Now, I'm only going to use the adjusted close, so I'll just get rid of these. Now I've got the dates and the adjusted close. They put them in backward order with the newest first. I prefer to have it go time going down, so let's sort that. Sort by date, oldest to newest, boom, okay. And just so I can remind myself what I'm looking at, it's Home Depot. Now these are the stock prices. I want to deal with the stock returns because, well, if I was pricing this in a different currency, that would change what these prices are. But if I do it as returns, it sort of ends up being like percentage change, like fraction of change. So I want to get, this is May 4th, Star Wars Day, last year. I want to get the return that I got over this time period. So if I would have invested $107.85 and bought a share on May 4th, on May 5th I could have sold it for, I would have lost money, I could have sold it for $105.89. So what did I make? Well, that's what I would have sold it for, that's what I would have bought it for. So that almost losing $2. But relative, so I'm going to divide it by the amount of money I put in, gives me the return. So a loss of 1.8% is what I would have made over that 1 day. That's our return. So this column is going to have our returns, our R sub i's. I'll just drag that down. Notice it goes to 253. Okay, so these are returns. Just Let's just look at them graphically. Just see a line. So it looks like they're kind of hovering around. There's like an average. Sometimes they're high and sometimes they're low. We're going to assume that they're distributed from a normal distribution with some kind of a average. Okay, let's figure out what that average is. Taking the average of these returns. Judging from the graph, I think it's going to be a positive number because generally the thing was drifting up. Yes, so on average, that's the average return per day. But if I want this to be a drift, a mu, then I need to quote all my numbers in terms of annual. So if that's what it goes up a day, and there's 252 trading days in a year, then I'm going to multiply that by 252. There's our drift. 24% a year on average is what it should go up. Then I want my volatility. Well, volatility is going to be standard deviation of the returns. Okay, I still have to scale that. This is my sigma. So what I've got now is daily. I need to scale that. So should that be bigger or smaller? Well, that's the spread over one day. The spread over a year should be larger. So I want to multiply this by, I want to scale it up. But it scales with root dt. So I want to multiply it by square root of 252. Oh, this is unusual that the volatility is smaller than the drift. Normally the drift is a smaller number than the volatility. So this actually, that makes Home Depot kind of a pretty safe stock to buy. All right, so I know what the drift is, and I know what the volatility is for this stock. I guess I'm interested. We're going to end up thinking that these returns are taken from a distribution. So let's see if we can just look at that distribution. Let's go back up here. I just want to grab a histogram of this. Okay, let's try it again. Histogram. Thin range. Okay, let's just see what this looks like. It looks like I shouldn't have gone so high, but we'll do a graph. A bar chart. All right, there it is. So those are the returns. I'm going to point at that and say, look, the returns seem to be a normal distribution. The average of this, the center of this normal distribution, this bell-shaped, this Gaussian curve, the average should be the drift, 0.23. The spread, or the standard deviation of it, should be, well, our volatility, the 0.2. So that means that if I needed to predict the return for tomorrow, I could pull from a normal distribution that has this average and this volatility. Of course, I would have to scale these volatility and drift back to daily levels. And then I could use that, a random variable, picking from this distribution would be a random variable, picking from this distribution would give me a random variable, and that would be like the daily return that I would predict for tomorrow. So by looking at real data, then we're trying to get an understanding of how the stocks actually move. Now, every assumption I make is close but not exact. One of the things that I'm pointing at this graph and saying, oh look, it's a normal distribution. It's kind of a normal distribution. Generally, these things have fatter tails than a normal distribution should have. But we use a normal distribution as an approximation, as a good enough, as a close enough approximation, because it makes the math easier later on. We understand normal distributions from our statistics class. This mu of 0.239 and this volatility, this sigma of 0.2, these would be the data that you could use in making your binomial tree from chapter 3. You could take these, this mu. You wouldn't need this mu, right? The drift rate doesn't make any difference in the pricing of an option because you hedge it out. But this sigma you could use from the data. So if we assume that our stock prices are picked from a distribution like a normal distribution, then we can think of them as start at the middle. We're going to call that S bar in a second. Start at the middle of the distribution and either go a little bit to this side or a little bit to that side. So there's a middle plus a little bit of error, and the error can be a little bit positive or a little bit negative. So where I'm going with that is Jensen's inequality. So then this is our distribution, a normal distribution of the returns. And we're going to think then that if the returns are normally distributed, then our stock prices are, if the returns are normally distributed, then our stock price is always what we expect the stock price to be, but maybe a little bit higher if I have a slightly positive return, or a return that's bigger than average, or a little bit lower if I have a return here that's slightly lower than average. So I'm going to think of my stock prices then. I'm going to Jensen's inequality. I'm going to think of my stock prices as the stock is equal to our expected value of the stock plus a little bit, this epsilon. And this epsilon could be positive or this epsilon could be negative, but on average it's 0. So the expected stock price then is this S bar. The expected error or difference between the stock and its average, the expected error, let's say, is 0, is the way to think about it. And we're going to call then f of s is going to be the payoff. We're looking at Jensen's inequality here. I'm out of chapter 4. We're looking at f of s to be the payoff of an option with a particular stock price. So the option could be a call or a put. And to examine this payoff, I'm going to write the payoff function as its Taylor expansion. So I'm expanding it about S bar. So if I'm expanding it about S bar, think of that as, in our standard calculus book, the A is where we would expand it about. So f of A, or f of S bar. And the next thing I need then is the derivative. The first derivative with respect to S, evaluated at S bar, and then times, well, it would be times S minus S bar, but S minus S bar is just epsilon. And now I need the second derivative. Well, no, I need half of the second derivative. So that's going to be epsilon squared, and this will be f of prime prime. So, and then what's the rest of it? Well, there's like third order and higher, so I'm just going to go dot, dot, dot. So now I've expressed the payoff function as a Taylor expansion. The next thing I'm going to do, I'm going to take expected value of both sides. So expected value of the left side. Now expected value, if I take the expected value of this whole side, because it's a sum, that's the expected value of a sum is the sum of the expected value. So I'm taking the expected value of each of these pieces separately. But S bar is a constant, so f of S bar is a constant, so the expected value of the constant is just f of S bar. So this stays the same. The expected value of epsilon f, well, again, S bar is a constant, so f prime of S bar is a constant. So the only thing that I have to take expected values of is that. Again, the second derivative is a constant, so I'm just taking the expected value of epsilon squared here, because that's a constant. And then there's some dot dot dots. Now, what do we got here? So I've taken, to get from this step to this step, I've taken the expected value of both sides. Now we're going to make the argument that we always make, that the higher order terms are too small to worry about, so I stopped writing the dot 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 there. I mean, these epsilons are small numbers that average around 0. So when I'm up here, we're epsilon cubed, and it would be a divided by 3 factorial divided by 6. It's a decimal cubed and then divided by 6 is too small. We're getting rid of it. And the expected value of epsilon is 0 from up here, so I can just dump this whole thing. It's 0 times the derivative. And this is what I've got. That read this as the expected value of the payoff. Read this as the payoff of the expected value, because S bar is the expected value of the stock. And now this is, well, I don't know, this is some number, maybe the variance divided by 2. It really, whether this is positive, whether this piece is positive or negative, depends on the sign of the second derivative. Well, let's think about a call option or a put option. A call option or a put option have curves that either look like this or look like this, but they're concave up like a parabola. Their second derivative is positive. Well, that means that this piece is a positive number. So I have to take the function at the expected value and add something to it to get the expected value of the function. That means that that side must be smaller. So here's Jensen's inequality. In English, Jensen's inequality says that the payoff at the expected value is less than the expected value of the payoff. All right. Did that happen to us when we did our one-step binomial tree? We'll have to go back and check that out. I think we'll find that it did. When we had the, I'll have to look at an example, but if it's 60% of the chance that the stock goes up, and now we'll have to just go back and take a look. We'll have to go back and look at an example, and you can verify that this Jensen's inequality holds. And Jensen's inequality is hinging on the fact that the convexity, that the second derivative of the option is a positive value. So let's go back to our Home Depot stock. What we're trying to do then is we're trying to get enough understanding of how a stock moves so that we can simulate it, so that we can model it. Here's our adjusted closes, and we did look at a graph that Yahoo made, but let's just look at our own graph. That's what it looks like. So if we could produce something that looked like this, we could say we were modeling Home Depot stock. Well, what do we understand about it then, or what are we assuming that we understand about it? We're assuming that, well, if I knew that the return of this, if I knew the stock closed on May 4th at 107, and I had a return of minus 0.01, then I would calculate today's stock price as equals to the old stock price times 1 plus the return times the return. And there's my 105. So if I could model these returns, then I could match the stock prices. And I'm assuming that these returns are equal to a little bit of drift. So this drift value of 0.23, oh, I got to scale it per day, so times the time step of a day, plus a little bit of volatility, times the square root of the time step. Oh, times a random number. And that random number, that x, well, let's call it an n, that random number n is drawn from a standard normal distribution. So our n's are drawn from a standard normal distribution with a mean of 0 and a standard deviation of 1. So all I have to do is pick an n, and that'll simulate a return. These returns here must have had n's already picked for them. We have to figure out how to choose a standard normal, an n from a standard normal distribution. Now the book does it by, in Excel, if I just go RAND bracket bracket, this gives me, that's a U. That's a standard norm, that's a random variable generated from a uniform distribution from 0 to 1. Every time I reload the page, it gives me a new standard normal distribution. But these are all uniformly from 0 to 1. I want a normal distribution. So what do we have to do? Well, the way the book deals with it is the book says, all right, I'm going to add 12 of these things together. So let's do it the book way right now. So now I've got 5 of these things. If I go, there's 10 of these things. There's 12 standard normal distribution, or sorry, 12 uniform distribution. Now each one of these, since they are picking a number between 0 and 1, they have an expected value of a half. So each one of these 12 rands I expect to be a half. So I add up 12 of them. My expected answer is 6. So if I take this and subtract 6, now I expect all the sum of the rands to be 6 minus 6. Now I expect this to be have an expected value of 0, and it will have a standard deviation of 1. This sum of 12 uniformly distributed random numbers minus 6 is like an n. It's close to, it simulates a standard normal distribution, so that's what I want to sub in here. So if I just take this and I'll make a bunch of them there. These are n's. How many n's? 1, 2, a bunch. There's like a dozen n's here, and every time I reload the page, Excel recopies it, but these should all be distributed from a standard normal distribution. That's all I needed for these n's. So if I wanted to simulate returns, it would be equal to this drift scaled by 252, that's the same thing as multiplying it by the dt, plus this volatility scaled by the square root of 252 to put it back to daily, and then multiplying it by this random this standard normal distribution. That should give me a model of a return. Oh, what am I doing? I got to lock down these 2's with the dollar sign, because when I copy and paste, I don't want to change that. So now these are all the returns. These are simulated, these are modeled returns. And what did I do with the returns over here? I took our, let's just take our starting stock price, and we would go equals this times 1 plus this return and now this is okay, that 107.85, I took that from here, that's a lockdown, that's a real number. These ones are generated at random every time, and we're saying we've modeled the stock price. So I could look at that and go, oh, that's one possible future. Each one of those is one possible future that could have happened from this stock price. We know the actual future that did happen, but one of these, it'll be one of these futures that comes up. So what do? Here's our formula. We just needed the standard normal distribution numbers, the n's. We used that by adding 12 u's together and subtracting 6. That gives us our stochastic differential equation, but our way to model the change in the stock price. So ds would be this change in the stock price. I would add the ds to the old value of the stock to get the new value of the stock. And it was mu s dt. S is the current stock price, mu is the drift. dt then essentially scales the drift to daily, so dt would be 1 over 252 if we're talking about daily, 1 over 12 if we're talking about monthly. And then here's the random portion, the volatility, sigma s dx. Oh, so these dx's are the random variables. Now the way I've written it here, with no time step, then these random variables, these dx's, the way I've written it here, are coming out of a distribution, are coming out of a normal distribution with mean 0 and standard deviation root dt. So the way I wrote it here, the time step for the dx's is in the random variables. The other way to write it, the more explicit way to write it, is to put the dt in with the sigma and then make the dx's have a standard deviation of 1. Those are both equivalent ways of writing for the change of stock. So then you would pick a random number, these dx's, those dx's are like the n's from the spreadsheet. We'd pick an n, a random n, we'd multiply it by this current stock price, root dt, sigma, we'd add our mu s dt, and that would give us our change in stock price. We would take the old stock price, so it would work like stock price new equals stock price old, the day before, plus ds. Is how we would simulate stock prices that have the same drift and have the same volatility as our data.